Okay, so today we are going to have a look at effect of the different manufacturing process on the materials. Today we are going to have a look at the machining. What does machining do and how does it change the properties of the material? Now, what is machining? It's a material removal process in which we use a sharp cutting tool to mechanically cut away the metals so we can get the desired properties, geometries, not the properties, desired geometry. Most common application is to shape metal parts. It's very versatile and accurate of all the manufacturing process because we get better surface finish, we get better surface tolerance, and you can have multiple different geometries can be achieved. Sometimes we cast the material and the shape is not required, not to the specs, so we do the machining process as a secondary finishing process. Now, machining process, we got the turning. Now, turning, boring, drilling, milling, planing, shaping, broaching, and sawing. Turning, now all these processes have different dimensional tolerances. For the turning, you all familiar with the turning process? Yeah, so because you might have done in level 3, the workshops and so on. So if you are doing CNC machining or lathe machining, you might have done the turning. The tolerance is 0.025 to 0.13 of the millimeter. Now, then we got the boring process. The tolerance is 0.025. Then we have a drilling process. The tolerance is 0.075. Again, we have a milling process which have a similar kind of tolerance to the turning, the top range 0.13 to 0.25. Then we got the planing surface, shaping, broaching, and sawing. So these are all different types of machining process, all have different dimensional tolerances and different function. Again, some more processes are there: turning, milling, boring, grinding, reaming, and honing. Okay, now just to give you an example of the machining process, another machining process, milling. Okay, drilling, boring. So you got different types of machining processes are there, so you can actually see. Skip that one. In a lathe machine, most of you might have used a lathe machine as well. When we put a specimen in the lathe machine, we set the speed, cutting speed, based on the material we use, based on the properties we want, based on the shape we want. Now, every tool has a maximum speed. If you exceed the maximum speed, it will change the properties of the material. So we're not going into detail of the lathe machine. No. Now, let's have a look at the turning process. In a turning process, we feed the tool is here, that's the tool. Now, the direction of the travel of the tool is along this x-axis. So this is a chuck, it's rotating in that direction, let's say it's anti-clockwise in this case. Now, the tool actually moves, the feed moves here. Now, the amount of the material that's reduced or the cut away from this turning process depends on the speed, how fast is n, the number of revolution per minute, per second, and the depth of this tool as well. So the depth of this tool, like how much is the diameter, the external and the internal, what is the thickness that's being removed. Then we have the MRR, material removal rate. is the volume of the material removed per unit of the time. Now, the formula is D average diameter equals to the outer diameter plus the finished diameter divided by the 2. If you want to find out how much material is removed in one revolution, that should be equal to pi d times the d. Now this d here, the small d, is actually the thickness, how much thickness it has removed. Now the material removal rate is going to be the volume of the material that's cut in one revolution, which is V, multiplied by the number of revolution, n, how fast the thing is going. So that's pi d average d, and that's Fn, which is the speed, how fast this is actually moving. Now, if you want to find the cutting time depends on how fast the tool is traveling. The tool is traveling, let's say, is at a feed rate of Fn. The cutting time t, that's not a minus, it's just a bullet point, so it's not minus t. T is L, which is the length, divided by the Fn, the cutting feed rate. Yeah, it's to do with that one. So this is the F is that feed rate, F is here, and the D is actually this thickness between the outer and the inner dia. DF is the final dia and DO is the original dia. Now in a turning process, let's have a look at the material. Now we put that tool here. The material is turned in, let's say in this case, it's anti-clockwise direction, and we just kind of remove the material. If we are trying to remove the material throughout the whole length, like a horizontal length, what will actually happen is the rate of the removal depends on the speed. It also depends on the depth as well. Now, the rate of removal is known as the feed rate. Feed rate is calculated, the rate in millimeter per rev. The rate at which material is removed is the feed rate. We calculate the feed rate by the speed of rotation of the lathe and the speed at which the tool is advancing towards the workpiece in a horizontal direction. The depth of the cut is determined by the cutting tool width. How deep it's cutting is measured by the cutting tool width. Now there are different types of cutting tool. They are made of different materials depending on the other material surface hardness and everything. Now, how do we hold the cutting tool? So this is a shank. We put the base, we call it seat, and then we put the lock pin, and then we insert the tool. And after that one, we put the clamp on the top, so make sure the tool stays in its position. Now, for the cutting tools, there are different materials. We use high-speed steel for the high roughness. They are resistant to fracture, and so on. Now, usually the high-speed tool, they fail as flank wear and crater wear. They do not have the hot hardness at high temperature. They lose their hardness. They do not have high hardenability. Yep. And they have limited wear resistance. Then we got the carbides, uncoated carbides, and the coated carbides. Uncoated carbide has high hardness over a range of temperature. We cannot, the disadvantage, the limitation is we cannot use them for low speed because of the cold welding of the chips and microchipping. The coated carbides, they have a good wear resistance and we can use in multiple applications. Then we got the coated carbides. They have good wear resistance as compared to uncoated. They have more frictional and thermal properties. Again, we cannot use them at low speed because of cold welding of the chip, which the chip actually welds to that one. Now, ceramic. Ceramic tools are used as a high hardness at elevated temperature. They have high abrasive wear resistance. But the issue with them is they have low strength and low thermomechanical fatigue properties. Then we got the BN, boron nitrates, or like cubic boron nitrates. They have very high hot hardness, toughness. If we want to achieve the maximum depth in a single turn, we use these ones. Now, they have less chemical stability at high temperature as compared to ceramics. Then we got the diamond, very good, but again the issue is they have low strength, and at high temperature they have less chemical stability, so they react at high temperature, so we cannot use that one at high temperature. Now, when we cut the specimen, so this is the tool, the gray one, and it's moving in the velocity, so you can see the V here. So it's moving with the velocity towards that axis towards the workpiece. TC on the top is the thickness. Now, when it moves, the bottom surface will be this rough surface. So that will be the rough surface. If we move it quickly, the surface roughness will be more. If we move it slowly, the surface roughness will be less. Now, to do with the temperature, this also changes the temperature. So this is the tool, the gray one. Now, this gives you like kind of the temperature gradient at different. The surface in the middle has the highest temperature, 700, because not only it's cutting, but it's because of friction there as well. Workpiece has the maximum temperature. At the very top, you can see around 600 and 500, they have a highest temperature. So they develop a temperature gradient. If the temperature exceeds the certain value, the finished workpiece will have different properties. It might have gone through quenching or normalizing, and which will have different properties. Now, this gives you an idea of the temperature on an effect of the hardness. Now, on the ceramic, you can actually see if I increase the temperature, the hardness value actually decreases. On this side, the HRC is a Rockwell hardness C. On here, it's a Rockwell hardness A. They are different scales. Now, if you have a look at the carbon tool steel, the hardness value decreases straight away when you increase the temperature. So at around 300, they have very low hardness. So we cannot use them for high temperature. Now, the modes of failure. Fracture failures, there are three modes of tool failure. Fracture failure, cutting tool become excessive or dynamic, leading to a brittle fracture. There is a temperature failure. That cutting tool temperature become too high for the tool material, and then there is a gradual wear and tear, which is over a period of time. Okay.